So we're looking at the Han-Kobayashi region where we're doing rate splitting here. So effectively we get, if you look at this picture, it becomes kind of obvious that we now have 2 users at every terminal. So it's like having a 4 transmit, 2 receive problem where each receiver is decoding 3 of the 4 messages. And some overlap because of course both are decoding the primed messages. Those are being decoded at both. But to get the rate bounds now, well, that's, so if we look at decoder 1, well, what do we get, right? So decoder 1 is decoding 3 messages, so how many rate bounds do we get? 7, right? 1 for every possible combination of error event. So here we get 7 rate bounds, which I don't want to write out. I guess I should use the non-German 7 rate bounds. Decoder 2, 7 rate bounds. This is a German 1, by the way. So the German 7 is this, which some people think is a 3, so it gets a little confusing. Anyway, 7 rate bounds. So there's 14 rate bounds in total, which are, so this stuff blows up in your face, right? But I mean, if you want to study this and understand it, you go through this, right? You churn the things through. Now, the thing is, the rate bounds are in terms of the subrates, right? R1 primed, R1 double primed, R2 primed, and these 7 rate bounds are in terms of R2 primed, R2 double primed, and R1 primed. And now what we want to do is say, well, now we of course have R equals R1 primed plus R1 double primed, and R2 equals R2 prime plus R2 double prime. Now with these 14 inequalities and 2 equalities, and then of course we want this to be bigger than 0, right? So that's another set of inequalities. You plug this all into your Fourier-Motzkin elimination routine and you churn it out, and you wind up with oh, and I should mention actually, of these bounds, there's some that we don't want. For example, the probability that these 2 are correct and this one is wrong, we don't really care about, so we could in principle throw it out already now. Let's see here. And then there are some that are redundant, so you could reduce it too. But anyway, once you do Fourier-Motzkin elimination, we get 9 bounds out of all of this, simplifying. And from those 9, 2 are redundant. 2 we don't really need through special tricks, so it gets complicated. I don't want to get into all that stuff. It's very specialized. So you wind up, in the end, we wind up with 7 bounds. So let me show you at least what 4 of these look like. It's just to, again, emphasize the shape of the region that you get in general. Just so you know what this Han-Kobayashi thing looks like. So here's rate bound 1. There's 1 bound on rate 1, which looks as follows. x1, y1 given u2. That shouldn't be surprising. Why? Well, this is just the piece that we decode from user 2, right? u2. That's the common piece. And this is just once we know it, we can remove that interference, and then we get this rate, right? And the rest remains interference, like this v piece will be interference, and we live with that. So it's kind of like a way of, combining interference and no interference. Anyway, of course we get the symmetric version, and now there's 3 bounds on the sum rate. So we're going to take a minimization of 3 things. These are a little harder to interpret, but anyway, let me just write the first one, and I'll just say there's 2 others. One is the symmetric version of this, and then there's another one. There's a second bound and a third bound. And then here are the funny ones. There's a 2R1 plus R2 bound, which has the following form. This one I'll write out, and I won't write out the second one, because it's just a symmetric version of it. And let me say one word about this. Anyway, you have this in the notes, so you don't have to write all this stuff down. And then there's another bound on R1 plus R2, R2. Okay, and if we look at this bound, just to make sure it can do a sanity check, here we have one bound for rate 1, another bound for rate 1, and this is a bound for rate 2, right? So we have 2 R1 plus R2, that kind of idea. Now, it's a little bit hard to interpret these bounds, but anyway, there's 1, 2, 3, 4, 5, 6, 7 bounds. And these 7 bounds correspond to 1, 2, 3, 4, 5 plane lines. So if I draw this, curves look like this. So this is, the first bound is this one, right? That's this one here. So this has slope 0. Then we have one bound here. This is slope 1, slope infinity. Then we have a bound on slope 1, slope minus 1. Slope plus infinity, well, minus infinity or infinity, whatever. And then you get these two other bounds, one which looks like this, which has slope 1/2, minus 1/2, and one bound which has slope minus 2. And just to make sure I get them, this is the R1 plus 2R2 bound. And this here is the R2R1 plus R2 bound. Okay, so that's the general form of the Han-Kobayashi region. Now, these two, like I mentioned, usually what happens is these two are further out than the intersection of these. So what at medium SNR, let me put it that way, we get regions like this. And these other two bounds are like here and here, so they don't play a role. So this kind of situation here happens really only in the case that the powers are really large, so the P's are really large, and the interference is very small. So there was some nice papers from, there was nice papers from David Che's group from around 2006 or 7, which first showed that this region is within 1 bit of a converse bound. The main contribution there was to characterize more carefully this regime where you do actually start doing rate splitting. And doing rate splitting only becomes interesting for the scalar Gaussian case when you're at high power and low interference. So if you're a little bit familiar with this stuff, you know about degrees of freedom. They defined something called generalized degrees of freedom, where what they did is they scaled the power and at the same time scaled the interference down. So the scaling has to do with the behavior you're talking about is when the transmit power goes up and at the same time the interference is scaling down. And that's where they found gaps between the outer bound and inner bound. So, and if you study these things, they become relevant when you have about like 30 dB SNR and 30 dB, minus 30 dB interference levels, that kind of level. That's when they start kicking in. And then they start going, playing a more important role the higher the SNR and the lower the interference is. Okay, so that's really all I wanted to say about the Han-Kobayashi region. I mean, it involves a lot of, in a course where I have more time, I might go through the Fourier-Motzkin elimination, but it's really a lot of, just cranking out the bounds and so on, so it's not that much fun. It's just a lot of calculations. Now, there's many other topics we could discuss. So that's all I want to say about interference channels. There's many other topics. The vector case is not very much studied here. So one reason is, I could keep going. Then there's interference alignment. That's where you have that starts appearing when you have 3 transmitters and receivers. There's which caught a lot of papers started working on that because it was a nice new result showing that at high SNR you can get half the degrees of freedom and so on. Again, unfortunately, these effects seem to kick in at very high signal-to-noise ratios. So there's, at the moment, I would say this has cooled off a little bit in interest because, for lack of an application, at least in the wireless side. And the second reason is what people are doing is, rather than operating like this, the way you should really improve things rather than doing, sophisticated interference method is you should let these guys cooperate, right? That's the approach, because it simplifies a lot of stuff. And now you can do broadcast channel methods, which are already or MAC, which are already complicated, but are at least simpler than the interference channel methods. And the gains are larger, right? So doing this, you put a lot of work into it, and you gain less than by doing this. So why not just go in this direction? And so most companies, 5G doesn't do this at all, right? But there's a lot of interest in doing cooperative communications, right? Building links between base stations, and then of course looking at various levels of cooperation, like slow cooperation, like you just pass the the long scale statistics, or a little bit faster you pass the channel state information, or even faster, the ultimate is to give the same information, the full information, to both, right? And then you can do full beamforming and all that, but there's various layers of methods that people are considering. So most people aren't really focusing on interference channels in practice. And I suspect that will stay that way because that's just the better approach, I think. Still, I think the theory, it's useful to know these things. That's the state of the art. And again, if you're a theory person or an academic person, then certainly this problem is really fascinating. There's still a lot that's open here. Also for vector channels, that's an interesting topic, I think, too. And also optimization tools. That's very practical, of course. So anyway, it still shows up a lot in practice, right? Because inevitably we can't do full cooperation, so then you'll still have interference playing a role. Any questions about this?
I just want to modify this. So in an interference channel, you both, let's say, two interferer case we are considering, so both the receiver will have copy of both the messages, right? It's whatever we are sending. Now, if I don't want that, meaning if I have some private messages also to send.
Oh, yeah.
So in addition to the interference link, I want to add in each of these blocks some private messages which I don't want the
other person. So if you wanted to do secrecy to this?
Yeah, I mean, what are these rates? I mean, like are these well defined, or I mean, do we know?
We can define them.
I mean, do we know the region? I mean,
no, yeah, it's a good question. So suppose we want, right, so what you're asking is basically what is the secrecy capacity of this? I suspect, given the number of papers appearing every year, I wouldn't be surprised if someone's at least looked at it, but I don't think a lot of work has been done on that. That's an interesting point. I mean, there have been a lot of studies on broadcast channels with secrecy, physical layer, security. I don't think there's been much here. But again, given the thousands and tens of thousands and millions of papers that appear every year, it could be some paper has already at least addressed it. I would, looking at the review papers might be interesting. So let's talk about, the next topic is relay channels, which is very different in style because this is our first channel, which is 2-hop, right? So we've all the channels we've been talking about until now have been 1-hop. So I'm using their terminology from the Elgamal-Kim book. So if you look at how they organize their book, they have one subsection on 1-hop channels, broadcast, discrete memberless channel, rate distortion theory, broadcast channel, MAX, broadcast channels, interference channels, right? Maybe channels with feedback, so sort of two-way could, I guess, fit in there too, although I think that they put later. And then they talk about multi-hop. So the relay channel is one of the most basic such models. So we're back down to one message, which will probably make a lot of people happy, right? We have only one message. And if we think of the classic point-to-point channel, we have one transmitted message, we'll have one output, we'll have, of course, 3 terminals in a moment, but let me just look at the first case where we have point-to-point channel, right? It's a classic Shannon model. And so what we add here now is that there's a third terminal, which is out here, and which is supposed to serve as a helper, right? So there's going to be a second channel output and a second channel input. of the relay. And here usually I draw this just as a delay element. And this here is just a delay element, just to ensure causality, right? So the problem is the same as always, try to find the maximum R for which we can communicate the message reliably to the receiver. The only difference now is we have an additional channel input, additional node trying to help, and the rules of the game are as follows. Of course, x1n is a function of w, right? So this can be chosen fully as a function of w. And the usual rule for the relay is that it's a strictly causal function. A strictly causal function. Right? That's the usual rules of the game. Now, there are variations on this. So there was Abbas El-Gamal and some of his students looked at relay without delay in one paper, where this could be a function of non-strict causal system. That's an interesting variation of the problem. You can look at, non-causal up to some delays. There are some cases that you can think of where this kind of thing might even be realistic. For example, if for some reason the path from here to here takes a long time, like maybe goes through some circuitous route, and you stick in a relay that can, has a much shorter path, right? So you can think of the following. I'm sending around here, but for some reason the relay is here, somewhere in between, and here's what this guy has transmitted. Well, maybe what arrives here is earlier than what arrives here, for example. You see, and if they interfere with each other, we can even start coding ahead of time, and you get into non-causal stuff like for the Gelfand-Pinsker problem. So anyway, it's not so easy to think of a case, but it's possible to think of cases where that might be the case. So the reason for studying this case is it's quite general, because even if the delay is 2 or 3 or so on, we'll always get the same capacity region. Okay, and that's easy to see, because all you can do is if the delay is 2, we can, just in principle, we could split those transmissions into like odd pairs of times and even pairs of times, and then operate the channel on every sub-channels, and then it becomes a delay of 1 again, right? So if we use the channel only every second time, 1, 1, 1, then if there's a delay of 2, well then it's like a delay of 1 for this channel, right? And so then we're just going to look at the channel in this subsets, and then look at the channel in these subsets, and we can separate them and get the regular theory for both, right? Because the channel's memoryless, so we can always do that. So that's why this case is interesting to study, because it covers all cases with delay bigger than 1. It turns out that if we start making the delay causal, then the theory changes, and it changes for every, anti-causal reaction step that you can do. You'll get a different result. But the nice thing here is we'll get the same result irrespective of what the delay is. So that's why we focus on this case. Okay? And also is somehow the one that seems to is the most natural, I think. Okay, now one thing that's useful to do here, just to make things very clear, I'll just do this now. I haven't really done this up to now, as I want to write the, another thing before I get there. Note that just like for the multi-access channel, we have 2 transmitters, and so we're again assuming some kind of synchronization between the 2. So note there's some kind of synchronism being assumed between the terminals. It is assumed as synchronism between, like, let's say x1i, x2i, y3i is assumed. The y2i doesn't matter so much, because after all we already have, just this assumption, right? So there's some kind of synchronism that the third output is really some function of the first and second and they're really appearing at the same time. In particular, if these are waveform channels, like wireless channels, then again we have these time shift issues that we have to think about. Okay, so let me write out the joint probability distribution function of the system then that's under study. And I just do this for edification, not for any other reasons. It's just so that we have a full idea of what the system looks like. W hat. So these are all the random variables in the system, right? W, x1n, y2n, x2n, y3n, w hat. And the Markov nature of this problem is as follows. We get pw, and here comes the encoding function. Now, I've written, well, let me just continue, px and yn, and now we'll have the causality that comes in. So we'll get the x2i given, ooh, I have to put the other one first. P of, well, no, it's okay, my apologies. Y2i minus 1, right? So at time 1, this is 0, so we're just sending something that's independent of the input. But then we get the two outputs. And then once we get the two outputs, we can choose the next input, right? Then we have y2 at time 1 in here for I equals 2. And then finally, after you receive everything, we do the decoding function, right? So that's the joint PDF. Now, usually, so this here will be some deterministic function, so there's no point in having randomized decoding. That's almost clear. Second, this thing here, so what does having a deterministic function mean? It means the probability is either 0 or 1 valued, right? So this is 0 or 1 valued, this distribution. Now here, this is, if I leave it as p, I'm effectively permitting randomized encoding. Now in some problems, randomized encoding is actually useful. For instance, for secrecy problems, it's actually useful to add randomization. The reason it's sometimes useful is because you'd like to, the channel that you might have some bad characteristics, so that if I add some randomization, I improve the characteristics to make them better for the legitimate receiver and worse for the bad receiver. But usually for most communication problems, actually for all that I know, using deterministic functions is enough. And that's not hard to prove. There's some simple ways of proving that. And for this problem too, you can easily prove that the optimal encoding functions, at least for the models, these discrete memoryless models, is just 0 or 1. So these are all functions. And this is what we, of course, have to design. We have to design this box. We have to design this box, which is the same as this function and the sets of functions. So this is all I. And of course we have to design the decoding function. So it's the red ones that we're interested in. Everything else is given to us, this. And of course the channel is given to us by nature. Okay, so let's do a simple example of a relay channel. And what I'd like to emphasize with this is, again, the generality of Shannon's approach to consider these kinds of memoryless channels. What's the simplest kind of relay channel I think you could think of? That's just a wired channel, right? Suppose we have a classic network with 3 nodes, 1, 2, 3. And suppose we have if we look at this, so we have 3 wires, right, that we've just put between 3 nodes. So this might be 3 computer terminals with 3 plugged wires. Well, then we have 3 channels, right? And in fact, the input of node 1 is actually a vector input because that node has 2 inputs, right? x1, 1, x2, 1 for every wire. This is y2, that's a scalar. x2 is a scalar, and what receiver 3 sees is 2 wires plugged into its computer. So we see y31 and y32. So what we're seeing here is that x1 is actually already a MIMO channel, a multi-input vector channel. And the output is again a vector of 2. Oh, 1, 1 and 1, 2. right? And I claim that this here is a special kind of relay channel that's memoryless, even though you may not guess so. But anyway, it looks like this. So the full channel looks like this: y1, y2, y3, given x1, x2. Well, this is just going to be a product. The way we're going to model this is just as a product of three independent memoryless channels, namely the first one, y2 given x11, times p of y31 given x2 times p of y32 given x12. Okay? And so in other words, this channel also falls into the class of relay channels, and I emphasize this because all strategies that we're going to develop here will apply to this kind of channel as well as Gaussian channels, as well as to any other kind of models, which is kind of interesting. We're developing theory for a huge range of problems all at the same time. Of course, that's what Shannon's point-to-point channel did too, right? It was developing theory for wireless channels, for copper channels, for photonic channels, for molecular channels, and so on and so forth, which is what makes it so remarkable, right? So it's very generic results, and all the strategies we will develop have some interpretation for every one of these networks that we're going to consider. Okay, so that's one example. It's sort of the classic one. Now, one simple result we know of already, and I discussed this at the beginning, if the capacities of these channels, even if they're noisy, is C12, C23, and C13, then it turns out that there's a cut-set bound that says the capacity is less than or equal to the min of the cuts. Now here's cut 1, message source sync on the other side. That's C12 plus C13. And here's the other cut, C13 plus C23. And it turns out not only is this a bound, but it's equal to, which is very easy to see because we already know max flow min cut from noise-free channels, and with noise all we do is we separate the routing and the... And by the way, here you're doing a rate splitting, right? Here a rate splitting is happening. We have a message, we split into two pieces, and we route it across both, right? So rate splitting isn't really something new. I mean, it's always something that's been done in networking forever, right? It's multi-path routing, same thing, same idea. Let's do the second example, and that's the Gaussian case. So AWN channel, and the classic, the simplest approach, I think, is to look at it like this. Here we have an x1, n, and the relay sees a noisy version of this, so let's just call that noise z2n. Then we go through a delay functions to emphasize the causality. Here we have the relay. It's receiving y2n, it produces x2n, and then if we're transmitting on the same subband, then we have here a y3n. Right, and this is then, yeah, well, let me leave it at that. Okay, so there's our model. So the channel is here. Here's the channel. There's my P of y2, y3 given x1, x2, and this now will have a joint Gaussian distribution, right? That's quite straightforward, so it's going to be Gaussian distribution, py3. Okay? Now, a couple of comments about this. First of all, if I leave it like this, the model is a full duplex relay, right? It's a full duplex relay, right? So let me write out the equations more explicitly. And you'll also notice that I haven't put any gains here, so usually you'll have some gain, like gains here and gains here and here, right? Depending on how things are geometrically. We'll do some examples with this. And so usually the models here are, these are both zero mean with unit variance, independent of everything else. And because I'm so if you look at what's happening here, this is what, without any further constraints, well, we'll have one constraint. It's going to be the power constraint. So of course 1 over n summation from I equals 1 to n of the expected value with or without expectation. Ki squared is less than or equal to pk. K equals 1 to 2. Right, so for both users we have a power constraint. Now without any other further constraints, you'll notice that at every time I, user 1, this should be a 1, user 2 can transmit something and receive something, right? Okay, so this is a full duplex model. This is a classic model that's been studied, was actually a full duplex model in information theory literature. Now, full duplex, of course, has a lot of complications with it. Either you do it with 2 antennas, one pointing that way, one pointing the other. Even then, you know, isolating the EM waves is not such an easy task. But that's been a hot topic in research, at least in the US and I guess in Europe also, for now probably 10 years. So I think that started around 2005. There was some groups that started getting into, can we actually build full duplex radios? And I think that's become like a full-blown research area also for people working on implementing things. Now, for many problems we have half-duplex constraints, so how can we build that? Well, there's many ways to model half-duplex. One is, well, just split the just do 2 subbands, right? Here we communicate in one subband and here in the other, right? That one's quite easy because then I would just make Y3 a vector and have 2 outputs, one with this plus the other, right? Or the noisy version from the relay. Or if we're using the full band for everyone, one way to bring in full duplex is to constrain the channel so we can build it directly into our relay channel, the half-duplex constraint. We'll just add the following constraint to the channel, namely that y2 is equal to 0 if x2 is not equal to 0. And if we can add that formally to the channel itself, right? So the reason I emphasize this now is just, I again want to emphasize that the theory we're about to develop applies equally well to classic wired networks, as well as to full duplex networks, as well as to half duplex where we have separated values, as well as to half duplex channels where we're operating in the one band and at the same time. Okay, so to all these cases, all the theory we're about to develop applies to all these cases. So both to half duplex and full duplex relays. The reason I emphasize this is that when I remember after I published my paper in 2005 on relaying networks, there were some criticism saying, oh, it's all only for full duplex relays, you know, as a way to say, this isn't so practical. And then I had to point out later, well, wait a minute, I mean, for half duplex it works too, it's a general theory. Then let's go to coding strategies. And we'll start with the simplest one. So the rest of the relay channel and also the rest of today, I think, we'll be talking about various coding strategies for relay channels. The first one is the simplest one, and that is something I've labeled in the longer course notes as symbol relaying. Which will include something that's for a Gaussian channel, sometimes called amplifier forward, or sometimes called amplify forward. So symbol relaying is a simple relaying strategy. Well, what can the relay do? It receives a signal, so the relay sends y, let's say 2I is some function of y to I minus 1. Okay, so all it does is for every symbol it receives, it applies a function to it and sends off something, right? The advantage of this is it's very simple, right? So this doesn't require a particularly powerful relay. In fact, it could even be passive relay. Putting mirrors into walls is a way of building a relay that's passive and requires absolutely no power whatsoever, right? I mean, so for instance, if you want to use visible light communications and you have problems with things getting blocked off, yeah, put some mirrors into the wall or something that reflects the light at those frequencies, and suddenly you get a scattering situation, right? Or the same idea with microwave communications. Maybe you want to, you know, in newer buildings, I know that this has been discussed. When you build new buildings where architects are aware that a lot of people like to use wireless communication, well, put, you know, materials onto walls or into paint that reflect signals in a good way for certain frequencies, right? It's one way to, you could potentially improve communications. And that's this kind of relaying function if you think about it, right? Okay, so if we're looking at additive white Gaussian noise channels, this becomes simple, right? So let's look at this. So what that means is y3i will be x1i plus some function of y2 minus 1, which is just going to be x1i minus 1 plus z2i minus 1 plus noise. So this will be the case for full duplex. Or for half duplex, we will get xi 1i plus z3i if the relay is listening, or if the relay is talking, we'll get y3i equals f of x1i minus 1 plus c2 I minus 1 plus z3i if the relay is talking. So this is half duplex, right? Just as two examples of what's going to happen. Now if we look at the full duplex case, so in both cases we want to design, now design x1n to maximize the end-to-end mutual information, right? I x1n to y3n, right? Or in other words, design x1n, I should say, and f. That's the problem, right? Now, so the nice thing about this kind of relaying is A, very simple relays, no coding, nothing like that. B, we just now have to optimize the input and the function, of course, but sometimes the function might be chosen for us. One interesting thing, though, is this channel here now has memory, right? Because here we have x1 at time I, and here we have x1 at time I minus 1. And in particular, we're going to be interested in linear functions, so we just get an intersymbol interference channel, and so we should apply water filling to this, like OFDM with water filling, right? Channel has memory. And in fact, in some sense it has memory for the half-duplex case too, although here it's simpler because, we're separating what this guy transmitted, and then the half-duplex case, so usually what you do with, what you often do is you half-duplex, you might half the time have the relay listening, and then half the time the relay sending. Oh, and by the way, this is a special half-duplex, I should mention that, with multi-hop, right? So with multi-hop. What I mean with multi-hop processing is I'm not sending anything here. So if I want to get rid of that, maybe I should write this. y3i plus equals x1i. So I don't have to be silent when the relay is transmitting, but for many relaying protocols, especially multi-hop relaying, usually you have a time-sharing device where either the transmitter is sending or the relay is sending, so you avoid the interference here. But I could add the interference too, of course. But anyways, that's why I add here with multi-hop. So you already see there's a lot of options, right, already, once you hit problems like this. So let's talk about this a little bit more and just compute some rates out of this, just for the simplest cases that are usually used in wireless networks. So there's a special case of this, and this is called amplify forward. Amplify forward, which is sometimes shortened to AF. Here the function of y is just chosen to be some constant times y, where c is chosen to satisfy the power constraint of the relay, is chosen to satisfy, to maximize rate, of course, I x1n, y3n, and to satisfy the relay's power constraint. Right? So that's a very common method that's been applied in a lot of papers. Again, very simple method. We can do suppose we consider this case, suppose we consider as an example the multi-hop with half-duplex. Where what I mean by that, it's not so precise, but what I mean by that is either the x node 1 is transmitting, or node 2 is transmitting, but not both. Okay, so what that means is, so in fact what I want to do is so I want to split time in half. Maybe I draw a diagram. So what I want, the scenario I'm considering is 1 can send to 2, and then 2 can send to 3, and we use both half the time, right? It's the usual multi-hopping approach, right? So half the time I'm going to send to the relay, and then the next half the time I'm going to send to the receiver. And while the source is transmitting, either the distance is too far that you can't hear anything, or the destination is just not listening. Okay. In this case, it's quite easy. We just get a point-to-point channel, right? Because through this function, all that's happening is the y3 at every second time instance. So this is at even times. At even times, we're just going to see this cx1i minus 1 plus c times z2i minus 1 plus z3i. Right? So it's just this function right here. This has just become a constant times this. That's what we're seeing, right? And so effectively, we just have a channel that is being used half the time. We pay quite a large price in rate by using it only half the time. But otherwise, it's just a plain old additive white Gaussian noise channel. Right? So we can compute the rates that we get with this. We can compute the rates that we get with this. So the rate will become 1/4, because we're using the channel only half the time, usefully, log of 1 plus the signal to interference plus noise ratio, but the signal power is c squared p1, and the interference is going to be c squared n2 plus n3, where here I'm assuming now, I guess I changed things to z2 is n0 mean n2, z3 is Gaussian with variance n3, right? So there it is. And we need to subject the c to the constraint that c squared p1 plus n2 is less than or equal to p2, right? So that's the power constraint of the relay, right? Because because, this power here, which is c squared p1 plus c squared n2, better be less than p2. And so if you do this optimization, you'll see that we want to get equality here, and so that rate will become 1/4 log, and the final expression looks as follows: 1 plus p1 p2 divided by p1 n2 plus p1 plus n2 times n3. Okay, where we used equality here above. Okay. Now, if we look at this a little bit more closely, we can say a few things about this rate. First of all, what isn't nice, of course, is the 1/4, but you don't really have much choice if you have no direct link anyway, right? So that you may not, you might be forced to use the relay, and this is just one strategy for communicating. Now, we can look at different SNR regimes. So suppose P1 is large. What happens? Well, if P1 is large, what we'll get is P1, P2, P1, N2 plus P1, N3. The P1 cancels, so we'll get 1/4. So the rate is approximately 1/4 log of 1 plus P2 over N2 plus N3, right? So if we scale P2, we'll just get that the signal to interference is noise ratio. Okay, well, that's what we get. So we're getting, we lose a little bit due to the noise. You'll get a similar result if P2 is large. Well, if P2 is large, let's see here. Oh, well, if P2 is large, then we'll only be, we should still be limited by P1. Is there a P2 missing in here? Oh, this should have been P2. That makes sense. So this becomes, that makes sense. P2, so if P1 is large, we get P2 by N3. Which makes sense, right? It's the cut, it's this rate here, it's the cut, right? Because if P1 is large, we can bypass the first one. If P2 is large, because I shouldn't have gotten infinite, I can't get infinity, then we should be limited by the first one, right? Because if P2 is large, we'll get P1 by N2, exactly. Right? But now if N2 is large, let's say, or P2 is small, if either P1 or P2 is small, well, it depends how things scale. But let's instead choose the noise to be large. Let's say N2 is large. Let's just make P1 small. If P1 is small, what we'll get is, things will start disappearing, right? So this number here starts getting very small, so then the rate will be approximately 1/4. If we're taking the natural logarithm, we'll get rid of that. Then we'll get P1, P2, and this term will disappear, right? So we'll get P2, N2 plus N2, N3. So that will be 1/4. The P2, let's see here, we can take out the N2, P1, P2, N2, P2 plus N3. Okay. So we're getting rates that aren't somewhere near P1 over N3 or P2 over N3. In fact, if P2 is also small, so if both are small, we're even getting a product of powers, which is really bad, right? Then you're losing a lot of rate. Okay, so if P2 also small, then the rate goes down a lot. Then R is going to be, R behaves as P1, P2 divided by constant. and that's really bad because it's squared power, and for low power, squaring the power makes it even lower, right? Meanwhile, what's going to be an obvious strategy here is we'll just hop all the information to here and then hop all the information to here, so we just get the minimum of the two. So in fact, at high power, that's exactly what we're getting. We'll just choose, we may be getting that. We'll just be getting one of the two, the smaller of the two S and Rs. And here, if we're using amplify forward at low S and R, it's really bad. Okay, so low S, the main insight here is that at low S and R, amplify forward is not very good. Okay, main insight. AF not very good at low S and R. And it might be reasonable at high S and R. Okay? Now the problem is for most devices that are cheap, like relays, you will have relatively low S and R because you don't want them to become active devices. They might just be reflecting, they might be cheap devices, and so on. So how can we improve this? Well, there's two basic methods to improve this. One of them is, well, we should change this function, okay? And so we artificially chose this function. The problem with this function is as follows. We're also amplifying the noise, right? So if C, anything we do is we don't only amplify the signal we want to amplify, but we also amplify the noise. So one approach, low S and R approaches. There's two approaches. One is choose nonlinear function, and this has been studied by various people not so long ago, maybe only 5, 6, 7 years ago. One group, so Mikhail Skoglin's group at KTH in Sweden did quite a lot of work on this. So they chose modulo functions, for example. Modulo some range minus a to a. So the functions are only linear in range, and then if the function is higher, you map it back, right? So that's one way, and that actually helps performance a lot at low S and R by doing this. There's another group, so one of my doctoral students spent a lot of time designing functions like this, so he was able to get kind of, I think, quite interesting results on the choice of that function. If you can write a optimization routine on the function and then find what kind of shapes it has, and it's kind of interesting, depending on the S and R, like sometimes the shape of the function, so linear would be this with some slope, modulo of course is this, right? But it turns out the optimal function, sometimes they sort of have these S shapes that you might even expect. And in fact, one version of that, one extreme version of that is that you have something you might call demodulate in forward. So you just do a hard decision at the relay. Right. Like for BPSK, for instance, or QPSK, we do a hard decision detection at the relay. And why is that interesting? Because it removes the noise, right? Now, even, of course, it has some error probability, but sometimes that is much better than using a linear function. Now, the second approach, basic approach, is to use something called Bursty amplifier in forward. And what is Bursty AF? Well, you don't send all the time. You collect only some small number of inputs, and then you send with really high power sometimes. Okay, and that's, of course, the trick of doing this. You basically convert low S and R to high S and R that way, right? You're effectively gathering energy until once in a while you burst the signal. Now, of course, that's not particularly good because you might be killing your pre-log for amplifying forward, so you have to test how well that works. But Bursty amplifying forward has optimal diversity properties at low signal to noise ratio, so it's actually a very good strategy to give you the best possible sort of outage probability rates and in certain scenarios if you're interested in that. So it's a good strategy for those problems.